So we'll get started in just a couple minutes. But yes, I can go through that concept problem after the lecture. Sure. Thanks. Morning, everyone. Good to see everyone here for our very last regularly scheduled lectures. So, at the end of the day, we will have finished off all the material you're responsible for the final exam. I'll make an announcement about the final exam in a couple days. But the general concept is that it'll be very similar to how we ran the midterm, except you only get 3 hours this time because you now know how to upload things. So it's still the same length, 5 multiple choice questions, 8 regular questions, for which is a 2-hour exam, but you get 3 hours to help you scan and upload and whatnot. And also, I'm going to put also an announcement up for a couple extra bonus lecture that's on material not on the final exam, but they're kind of really good topics that you kind of need to cover, except that we don't have time for it. One of them is the electromagnetic wave and Maxwell's equations, which is basically what this whole course is building towards. Unfortunately, we're out of time. And the other one's on AC circuits. So that's particularly important for all you engineers out there, especially your electrical and computer engineering people moving on to future courses. So you can, I'll post up a certain time on that, or you can just watch it over the break, because of course everything is recorded on YouTube. So back to today. They were finishing off inductors and really briefly going through transformer because it's super simple. So inductors are kind of what happens when we ask the question, what happens if we connect a coil in a circuit, right? We've dealt with coils before. We just assume that there's some current through them, and we know that they create magnetic field and whatnot. What happens when we include such a thing as part of a circuit? Well, what's going to happen is, as we connect this battery, we're going to drive a current, right? And this current will then run through my coil, and then by the right-hand rule, we'll find that we get some more or less uniform magnetic field inside. Based on this expression, right? Directly proportional to the current. But there's an extra thing that might happen here. Because at the moment we switch on the voltage, right? The voltage changes from nothing to something. So you have a change in V, which will result in a change in current, which will then result in a change in your magnetic field, which then gives us a change in your magnetic flux through each individual loop of this coil. You can use M or B for magnetic flux. Then by Faraday's law, you would get some EMF because of this change, which then in turn acts as a voltage, right? And by Lenz's law, it would oppose this original change. So now that we have a good understanding of Faraday's law, we can see how this whole thing kind of goes in the loop. And that's why we sometimes call this phenomenon self-inductance, right? We're inducing an EMF because of all this magnetic induction stuff. And it's kind of doing it to itself, sort of thing. The textbook also covers this idea of mutual inductance, which takes place over with two separate circuits, but we're not going to go into that in any depth. We're going to focus on this self-inductance, or in most cases, we just call it inductance. The actual magnitude doesn't have to be the same, right? Just like how with the dropping magnet last time, you don't necessarily always get the same. It doesn't completely cancel out the change. But there are certain circumstances that we can ideally say for a short time that it does, and we'll get to that. But the voltage created does in fact oppose whatever change that you're trying to impose on it. So again, putting these all... Oh, before that, let's show you a quick video on kind of what you can... Just to give you a more visual idea of what's happening, I guess. So, in fact, all this thing happens so that you're opposing the change in the voltage, therefore opposing the change in the current, right? Because you don't want the magnetic field to change. That's what you don't want to change ultimately. So really, you're trying to maintain the same current. Well, let's see what happens in a circuit with a fairly big inductor then. So I'm going to show you just part of this clip. The link to the entire video is in the video description. And Physics Girl does amazing things. So I invite you to watch the whole video, but here's the highlight. They have a particular demonstration with a big giant coil that produces a very big magnetic field. But this coil, of course, also acts as an inductor. So here we go. Boom, right? You see that big giant spark, right? is from turning off the current. So when we remove that switch, what we're effectively doing is, let's get back to someplace I can write. When we flip the switch, right, if we have a switch and we flip it open, what we're doing is we have some kind of current. Actually, technically, we have some kind of voltage that was being supplied, and as soon as we flip it, it drops to 0, right? But the current is sort of doing the same thing, right? So if the current is going to change vertically like that, that's an infinite slope. So we have a huge change in current, and therefore a huge change in the flux, and therefore we can get a huge amount of EMF induced. In fact, as much as needed, that was able to, remember the dielectric breakdown of air? It was able to create that much voltage within that gap to make that spark. So an inductor tries to maintain current to the best of its ability. So let's kind of put this in a little more systematic way, right? Self-inductance. What is self-inductance? You have some kind of change in current, which leads to, in the coil, some kind of change in magnetic field inside the coil, which then leads to some kind of change in flux, magnetic, in that coil, which induces some kind of EMF, which is a V, which then in turn affects the circuit and changes the current. Right? You can see how it's sort of circular like that. So let's see let's do this whole analysis with, say, a long straight solenoid. Right? This in effect is the simplest case, right? Because inside a long straight solenoid of potentially infinite length, the magnetic field is uniform. That's why it's very much preferred. But it doesn't have to be that one, and there's reasons to use other shapes as well. But this is kind of like the case, similar to like your parallel plate capacitor, right? Uniform magnetic field. Simple, easier to calculate. So you have your Faraday's law, which is that. And so your delta V is equal to negative E d dt of the flux dot dA, right? And within a particular coil of a particular loop of the coil, your magnetic field is created perpendicular to the surface or parallel to dA. So every single point parallel to dA. And we also talk about how the size of the magnetic field is uniform across the entire cross-section based on what we did with Ampere's law. This allows us to simplify this lovely integral into B dA, magnitude, so that's just B times A, right? Then we ask ourselves, which one of these are actually changing in time? Well, the area is not going to change because the coil is not changing size. So that can pop out. But then B is given by, B is also given by mu naught and I. And it's just like how the area is not changing, the loop density shouldn't be changing. It's not like we have a slinky that we're playing like a harmonica or whatever. And the mu naught is definitely a constant. So what we're left with is that, and all these comes outside, right? So you got mu naught and A times di dt, right? Which could change. Your current could change. And so now we have a sort of relation for things that refer to circuits, voltage on one side, current on the other. And we have a bunch of more or less constants in time based on the geometry of my coil. So similar to how we encapsulate all these geometric properties of, say, a capacitor and call that capacitance, we can likewise make up a name for this thing and call this inductance. With the symbol L. And the unit for inductance is measured in H henries. And so basically the expression for a long straight solenoid is L is equal to, notice how N, we have big N and little n, so we choose one or the other. So you can, if you use big N, which is a total loop, you get N squared mu naught A over, let's say, the length L, right, just to not mix up big L and little l. And N shows up twice because it's involved in creating the magnetic field, and it's also involved in Faraday's law with the number of loops affecting the induced EMF. And then another form, if you want to use little n, you can do that, which then multiplied by n in the end, right? They're equivalent forms. It's just one uses loop density and the other one. Okay, addressing some question. Let's do the easier one. So the current can only the current can change. In most general case, yes. When you have a set when you have a set inductor that doesn't change in size or shape over time, which is in the case of most circuits, then the area, the loop density, number of loops, and the length are not expected to change over time. And then for Matt's question, why changing V is equal to the equation of EMF? I'm not sure what you mean there, Matt, because Faraday's law tells us, when you talk about the change in V, well, this is not really the change in V. This is potential difference, right? It's a difference of the potential between 2 points. So you can just treat this as V, right, if you want. In most circuit analysis, we just use V instead of delta V. And like I said last week, EMF, it's basically voltage. There's no real practical difference for our purposes. Okay, what are we confused about? Okay, that might be something we can do over office hours. So just maybe after the class, email me. We can go through that offline just so that I can get going. So yeah, so please contact me right after the class, and then we can start a separate Zoom session, and I can go through it with you then. So by defining this chunk of thing as V, right, we end up with the expression that the voltage or the potential difference across the inductor can be expressed as that. So now we have a circuit element that doesn't so much, its behavior doesn't depend on, say, the current, but rather the change in the current. So why I became di dt? Well, this whole flux term, which is this thing in here, is caught behind the time derivative. So everything that is constant in time gets to come outside, but then the current is not guaranteed to be fixed. So here's how inductors basically end up looking like. Most inductors really just look like a coil, and oftentimes there's some kind of iron core, right? Because we talk about how the iron core increases the magnetic field effect, and likewise we're going to make use of that also here. At this point, there's usually some, well, I got a number of them at this point actually that dealt with relating capacitance and inductance, because it seems like they are doing fairly similar things, right? They both kind of store up energy somehow. And so so I'm going to try and clear that up by doing a compare and contrast. So in circuit analysis, David, with we don't actually necessarily go into the detail of how the coils is wound, so we don't actually apply Lenz's law directly. We just know that whatever happens, the resulting EMF will be in the opposite direction as the change in current. So that's why we put the negative sign there, and we kind of abstract that sort of away for the sake of simplicity in circuit analysis. And it works. So you don't need to use Lenz's law every single time. So let's compare and contrast inductance and capacitance. So quickly a review of capacitance. Right, a capacitor, let's see, I can probably put it underneath. A capacitor will kind of like this, and then over time you build up some amount of charges on the one side versus the other. So then you end up with some electric field in here, which is what we're saying that the energy is stored within. Its governing equation for the capacitor is the voltage across the capacitor is Q over C. So because charge is conserved, that over time, unless you connect it and let it discharge, it tries to hold a certain amount of charge and therefore hold a certain amount of potential across it. Let's see how it plays out against the inductance. So the inductor it builds up a current, right? It builds up a magnetic flux inside the loop, which then maintains the current through Faraday's law. So it builds up a current, and then in turn stores the energy in magnetic field instead. And the governing equation for this is that V is equal to negative L di dt. And what it tries to do then is tries to maintain the same current. So in many sense, they're kind of like two sides of the same coin, right? Capacitance works with electric field and maintains voltage. Inductance works with magnetic field and tries to maintain current instead. Another key difference is, notice that we have charge here. The charge is a time integral of current, right? Because current is dq dt, right? And so the other thing that's weird with it is that inductors works off of the time derivative of current, whereas capacitance works with the time integral of current. So that's, again, another way to see how they're very complementary of each other. So this kind of leads into how we come up with the inductance of a certain geometry. So let's look back at the method we used for capacitance. First step, we take the two conductors and we say, oh, there's Q on one plate and negative Q on the other. Based on that, we do whatever we have to do to find E, be it integration or Gauss's law, right? And then once we have the E, we can find the potential difference using the integral of E dl. And then once we have this delta V, we take the Q divided by delta V, and then the Q should cancel out. We do a very similar step for inductance. In this case, we're going to assume a certain current instead. In fact, we're going to assume a certain current that changes over time. But we'll just put I for now. Based on that current, we find the expression for my magnetic field. Once we have the magnetic field, then we find the magnetic flux. By taking the integral of B dot dA. And then to get L, we take Faraday's law. Or well, let's just use V. Forget the whole EMF thing. Right? And chances are once you get to this step and fully expands what B is in terms of current, you can relate this to that. The only derivative left you should have is di dt, and then that should cancel out the I to begin with. So to find L then, you take whatever expression you have here, that's an expression, and divide through like that. Right? You take whatever V you have and divide by di dt. And we went through basically that same process up here, right? Because we assume some current, and so we find that the magnetic field here is expressed by that. Then we stick it through my Faraday's law, and because a bunch of things were constant in time, they all came out, and so we take this expression and divide and cancel out the di dt, and whatever's left is basically your inductance. And again, oh, I forgot the square here, so make sure you put that back in. So that's how we come up with the inductance based on the geometry of the coil. And that's one type of problem you'll be dealing with. Another types of problem you're dealing with, just like in the capacitor unit, is what happens when you put them in circuits. Remember how we have a few types of problems? Now, we're not very rarely do we have a circuit with just pure inductance, just because the wires that make up the inductor often has a little bit of resistance anyway. So although you could do the same thing with series and parallel connection, you won't see many problems dealing with that. So most likely we're going to be dealing with some combination of resistance and inductance in the circuit. We call those RL circuits. And like in the back up. So what do I mean by assuming I? So just say that there's some current value I going through your coil. Just like how we assume that there's plus Q and positive and minus Q on the plates. And then you carry through that I throughout your analysis, and then in the end, hopefully it will cancel out. So, let's see. While mathematically this is true, usually what I do is I just take the time derivative and get that expression first instead. So don't treat this like a fraction because it is a derivative, right? Just think of this as my v, right? Find out your v as an expression, right? And then divide out the term that involves di dt. Now, if there's still specific question about this, I'd be happy to kind of go through kind of the entire process with the solenoid, once again doing it step by step like this at the end of the class, if you will stick around. But let's just get through the material first, and then we'll come back to this. So, LR circuits. So it's in a combination of resistors and inductors. So just like how we did with RC circuit, there are two general classes that we'll be dealing with, right? There's because it does involve differential equations, right? We're going to stick with one type of problem where we're looking at the extreme cases, right? After a long time or just after things get switched. And these are, in the capacitor, we call that fully discharged or fully charged. The wording in inductors is a little different, right? Because we're not dealing with charges, we're dealing with current. So we say energized or de-energized. Those are the words we're going for. And then we look at the extreme and then replace that inductor with some other component, and then we can do the rest with just a pure simple resistive kind of circuit, at least at that time. So what do we replace it with? So in the case when we're energizing, or it's similar to charging, right? So we start fully de-energized and we're connecting the battery to it or something. immediately after connecting your source or whatever, right? Inductors has this thing of it tries to keep current the same. So before you connect the switch, there was no current through the coil. So right after you do the switch, it's going to try to maintain it at no current. Now back to David's earlier question about does it always completely cancel out? Not always, but at this very particular time, you have no voltage and then some voltage, right? So this is where your di dt is basically infinite, right? It's a vertical slope. So if it's a vertical jump, so the slope is infinite, so therefore you're going to get as much EMF as needed to have I equals 0. So we're kind of guaranteed that immediately after connecting the V, you have, for that split second, that your current is in fact 0. And if you have a circuit component where there's no current through it, then you can replace it with an open switch, much like how we dealt with a fully charged capacitor. After a long time, as time goes on, the current becomes stable, right? After a long time is our way of saying as it reaches equilibrium, if the current is stable, then di dt would be 0, right? Current's not changing. Therefore, your EMF is in fact 0. So the voltage across your inductor is therefore 0. So therefore, a circuit component with 0 potential difference, then we can replace it with a simple wire of no resistance, which is just like a fully discharged capacitor. You see how it's like flip from the capacitance case? So for the case of de-energizing, again, you're going to get so if you're like disconnecting a switch or something, again, you're going to get a big jump downwards this time. Again, vertical, infinite, so you have as much you're going to have as much as much EMF as you need to keep the current same as before. So you replace the inductor as a source. Yes, that is V subscript L. That's a terrible V subscript L, but you're going to keep the same current as before. And depending on how much resistance is in series with that inductor, you would need however much voltage to maintain that current. And you'll get as much voltage as you need to make that happen. So if you're given a mixture of resistance and inductance in the circuit, and we talk to you with the same kind of keywords like immediately after or after a long time, fully energized, fully de-energized, you kind of replace it with the right circuit component, and then you go through with the whole analysis. very similar to our RC case. And very similar to our RC case, for all the intermediate stuff, the transient, so to speak, behavior, we only deal with the most simple of the simple RL circuit, and which is one inductor and one resistor in series. And so if you do this loop rule, right? Oh, by the way, that is the circuit schematic symbol for an inductor. It's not the sharp squiggly like a resistor. It's like a bunch of bumps, sort of like a coil, but I guess they didn't want to draw circles or whatever. This is the case of energizing, of course, energizing. So while you're building up your magnetic field, at the very beginning, you're going to get when you first flip on the switch, right, the inductor is going to try and maintain the zero current by so this is current over time, this is voltage over time, by providing as much or as high as possible a voltage, right? So you have VO. And over time, this is going to slowly come up until it reaches some equilibrium, and then this crashes to zero, right? So these are the rationale. And if you would look at the differential equation as a result, so you have plus V minus L di dt minus R times I, right? Those are the characteristic equations for each of these components. Back to the same loop, equals 0. Right, again, you have a first order linear differential equation. So you want a function form that looks kind of like its own derivative, which is your e to the t. So it's no surprise that the current here would have this form, right? It starts high. It starts low and slowly reaches some maximum equilibrium point. Call that max. And here, tau is not R times C anymore, it's L over R. And V goes from some high number all the way to 0, so that's V equals to V naught e to the minus t over tau. And if you're de-energizing, we basically remove the battery. But what we have still, and not immediately clear, is that at the time we remove the battery, there's a certain amount of current already going through the coil. So then the coil tries to maintain that current. So you can start at some high current, and slowly over time, as the energy gets dissipated, drains down to 0, and then you see that it becomes more or less flat. And so that's why, likewise, you're going to have a bunch of voltage to start with, and then your induced voltage drops to 0 as your current becomes stabilized. So then in this case, both of these would be your decaying exponential with the same tau. So very similar to your RC circuit case, all you're kind of doing is working what tau is and then picking out the right function, whether you're energizing or de-energizing, talking about current or voltage or whichever. Then the next question is, I guess, what the heck happens when you connect a inductor with a capacitor? And these we call LC circuits, right? No surprise, which is different combinations of letters. So let's show you this simulation that I've got here going. With FET, so we're gonna charge up my capacitor, right? If you have no charge on anything, then no matter what happens, you're just connecting to things that doesn't do anything together. There's no fun in that. But now we do have some charge on the capacitor, okay? And these little blue balls here, they're supposed to be electrons, so they're gonna flow, I guess in this case, clockwise. The current, conventional current, would go counterclockwise, but what you'll see is the electron flowing clockwise. And now I have a pause. I'll connect this now. This is disconnected. The battery's out of the picture. So then as the current flows through, you're going to end up discharging the capacitor. No surprise there. Boom, 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 boom. But now that the capacitor is charged, you might think that things might stop, but it wouldn't, because there's still there's current now going through this inductor. And the inductor will try to maintain that same current in the same direction. So what's going to happen is it's going to keep pushing charges until it builds up negative charges on this plate over here. Until the inductor is out of energy and you're quote-unquote fully charged again, then the capacitor will start pushing things back the other way. And then it'll overshoot because of the inductor being there, back and forth, back and forth, back and forth. If we put a ammeter in there, you'll see that it kind of goes up and down. This is absolute value, so if we plot it, let's plot it. So the current over here, you'll see that it does sort of a sinusoidal thing. Look at the voltage of the charge across the capacitor. You see that it likewise does a sinusoidal thing. Yes, as it happens, for the energizing and the decharging cases, they both kind of start high and go and drop. Now the direction might be opposite, but if you just talk about the amplitude, yes, it starts high and drops to zero over time. Okay, so back to this. Now you can see that both the V and the I, they're both sinusoidal, right? And that's why oftentimes we call this combination of things an LC oscillator. It oscillates back and forth. In fact, I'll show you that the function of that will, in a sense, yes, it is an AC current, yeah. It is a sinusoidal current that goes back and forth. So we call this an LC oscillator. And in fact, it kind of bounces the energy back and forth between magnetic field and electric field. If you were to look at the loop rule, right, you have your capacitor, which is supplying the initial voltage, let's say. So it's Q over C minus L over di dt is equal to 0. That's the loop. But I is equal to dq dt. So then what you have here is you have actually the second derivative of charge. And we end up with what we call a second order linear differential equation. You might have seen this in your simple harmonic oscillation unit when we had to deal with very similar looking differential equations. We are looking for a function that has a form that is pretty much the same as its second derivative, which would be your sine and cosine functions. So you can end up with that your charge is some amplitude times, let's say, sine. I mean, depending on where time equals 0 is, there's offsets and whatnot. But the charge, and therefore the voltage across the capacitor, would have this form, right? And then the current, let's say through the inductor, therefore through the whole circuit, is a derivative of that. So that has a cosine function. In any case, the really important thing is, what the heck is this omega? And this omega would be 1 over the square root of L times C, which is not surprising because if you have a big inductor or a big capacitor, it would take longer time to oscillate. You would be oscillating slower. So then all the things you kind of learn about harmonic oscillation from 1125 would still basically apply here. You can talk about frequency and period and all that stuff. Notice how this is the ideal case where there is no resistance in the whole loop. So technically it will never stop. It's just this. It's like oscillation with an ideal spring. It should go on forever in the ideal case, which is a great time to bring up the next logical step to this whole thing. What if we toss a resistor in there? If we toss a resistor in there, we call this now an LRC circuit. Right? And what this does is it dissipates, I think I'm saying that right, dissipates energy from the circuit. So you're going to change some of the electrical energy into heat and thermal energy. Which is the same as, if you remember from 1125, if you did damped harmonic oscillation, this is exactly what's happening here. You're taking some of the energy over time, so then yes, the current, goes up and down, but over time, the amplitude is going to get smaller and smaller and smaller and smaller and smaller. Yes, so in the real world, there's usually some non-zero resistance within the circuit, even just in the windings of the wires of the solenoid. Then over time, it does dissipate over time. We're not going to go through and do all the detailed math because you haven't really covered differential equation formally yet. So as long as you understand qualitatively what's going on, that's kind of what I'm aiming for. So LCR circuits. All right, so then the last topic of the day and the course is transformers. We kind of toss this in here just because the math and the analysis is super simple and that it is often used in everyday life. Of course, not this cool looking transformer is what we're studying. Most transformers in everyday life looks much more boxy than that. The inside kind of have components like this. In fact, most of your electronic device is the dissipates energy part of a wire. So back here, I've replaced that wire with an actual resistance. And that's kind of in the model what's doing the dissipation. So in most of your electronic device, you would have a thing like this inside. Most of the weight of like your older TVs and whatever would be in this transformer bit. What a transformer is really just a couple coils of wires placed close to each other, and it does some magical thing due to magnetic induction yet again. What it does, a transformer converts voltage to different values. It can also convert current to different values. It does it at the same time. But the key thing is the voltage must be changing all the time, because this whole thing relies on Faraday's law. Right? If there's no change in time, everything kind of shorts out and nothing happens, right? So the voltage must be changing all the time for these transformers to work. So very naturally, with a sinusoidal AC kind of voltage source, it works very well with transformers. While it is still possible to build a DC transformers, it is way more complicated than the AC case. And so that's part of the reason why a lot of our electrical generation and transmission and whatnot is done in AC. So how does it actually work? The basic principle is that we have two sets of windings. We'll call one primary, so that's why it's P. We'll call this secondary. It's really just another fancy word for, say, input and output sort of thing. The primary is the one that's hooked up to, and this is a symbol for an AC voltage source. Hook up to the power, basically, the energy input. And then it goes to this coil, right? Now, there's some changing voltage happening here, which leads to some changing current going through here, which leads to some magnetic field being created this way, which has a change, right? That changes in time. This basically metal construction frame here, we talked about how it channels magnetic field, so it channels into here, which then results in a changing magnetic flux in the secondary coil, ultimately leading to some EMF or voltage being produced on this side, which drives a current. So as you can imagine, the more loops you have, right, because of Faraday's law, the more loops you have on the secondary, the higher the induced EMF is going to become. So that's why the very simple expression for transformer is that the secondary, the size of the secondary voltage, and because we're dealing with AC, these are amplitudes actually, often. And if you come up on my AC lecture, then we might do RMS voltage as well, which is the same thing. It's related to the number of loops in both the coils. And that's a very, very simple analysis that you need to do for transformer. But energy and power is conserved, so whatever input power you have must equal your output power. So you're not necessarily gaining anything by stepping up the voltage, because you end up stepping down the current, or vice versa. So this extra expression allows you to then relate the current as well. So that brings us to the end of the course for now. So thank you very much for sticking with us through the bitter end. And despite all the weirdness that's happening right now, I'm glad you're able to join us for this last lecture. What do I mean by amplitude? So this here is an AC voltage source, right? So you can't talk about one specific number for the voltage because it goes up and down, up and down, up and down. But we can talk about how high these up and down goes, right? That's the amplitude of the sinusoidal function. So I'll be posting up the solution to all the midterms as well as some practice finals and the quiz. I'll make some announcements about the final exam and how it's going to be run. I'll make some announcement as to the couple bonus lectures that I'll talk about. And we will open up to questions. So William had one question. So let's do that one first. But yeah, keep the questions coming. Where is it? It's here. Okay. Okay, let's finish this question first. So this is the right one, I presume. Let me know if it's not. So it says that inductance. So we're aiming for a certain inductance, right? And we have relationship between the inductance. Oh, right. Let's do that. So we're aiming for a certain amount of inductance. And we have an expression with the inductance of a long straight solenoid, which is, where is it? Let me look it up. There it is. So the L is equal to, I guess, let's use this form for this time. Because we want to kind of keep the N and the L separate. So what we're told is we have a certain length of wire. That's not the length of the solenoid. Oh, geez. Terrible nomenclature there. That's not the length of the solenoid. That's the length of the wire that as it goes around and around and around and around. So what we know is that if you have A as pi r square, then each loop is 2 pi r times the number of loops is equal to 1.07 meters. So then we can solve for r in that sense. And then we stick r squared back in, and thankfully the n squared cancels out. So then we're only left with one single variable, which we can solve for L. And while I'm here, Finn's question about welding machine. It depends on which kind of welding machine you're talking about. Some welding machine needs like an arc welder. You gotta make an arc, right? So to have an arc, you need to have high voltage, right? For resistant welding, like a spot welder, you would need high current to get power is equal to I squared times R. So it depends on what kind of welding machine you're talking about in order to get if you want high voltage or low voltage. But yes, in order to switch up or switch down, chances are you would use some kind of transformer. And yes, I did do a co-op job once upon a time in a welding company. That's why I know so much about welding, more than you would expect. Since there was some confusion earlier while I'm here, I guess I can just go through the steps for coming up with a inductance of a solenoid yet again. So step one, so we have solenoid, right? This solenoid has certain things given, right? We have a certain length, we have certain, let's just go for area, right? Because it's simpler, right? There's a certain area in this thing, that's all, and certain number of loops. These are given. So step one is to assume some I. So we have some unknown I that's going through here, which therefore means whatever magnetic field inside is mu naught times N times I. Or you can say mu naught N over L times I. The magnetic flux, because of the geometry of the whole thing, right? Each of these individual loop, right? If you look at it head on, in this case, now, let's say we're looking at it like that. Let's say the current goes like this, right? The magnetic field is going to be coming out of the plane of the loop. So we again have B is perpendicular to A. And then also because of the solenoid, we know that the magnetic field magnitude is the same for every single point, right? So then this flux integral simply becomes B times A, which is therefore mu naught N over L I times A. Right, I'm just replacing the flux with that expression that I got, carrying with it the I still. I still have no idea what I is, and hopefully it cancels out towards the end. And then mu's not supposed to change in time, so that can come out. Your number of loops and your loop and your coil length and your area, those are geometry things. Your thing doesn't change shape. So then, therefore, what you're left with is negative N square mu naught A L di dt. So that's my V. So then the last step is we take the L, because we also know that V is equal to negative L di dt. If we take the L and take the V and divide by negative I di dt, then we have negative N squared, what was it? Mu naught A over L di dt divided by di dt, negative. So these goes away, and then as expected, the I cancels out, And so we are in fact left with the expression that we're expecting, like that. Or you can say little n. Oh geez, I keep using big L. My bad. Let's use little L. Little n squared, little L, mu naught times A. Let's change the thing before. Little L, little L, little L, so you don't get confused. So hopefully that clears things up for people. If you have no other question, thank you for your attention, and we will see you around. Yeah, that's really my bad. So, big L here stands for the inductance, and little l, now that I've corrected it, stands for the actual length of the solenoid. Okay, we'll call it a day here. So, thank you again. Signing off.